So, very warm welcome to Karen Crowther. She's based at Oslo. It's a big pleasure for me to have her here today at our seminar series. She is an expert she's expertise on the big question of emergence in quantum gravity approaches. So I am glad to introduce her today, and also to welcome all the participants to the talk as below. So before, synchronic and diachronic conceptions of space-time emergence. Thank you, Karen.
Thanks. I'll just share the slides in the chat as well if people want them. But yeah, I'll just comment on this bubble image. It's supposed to represent the quantum foam that maybe underlies space-time. So just thought I'd make a nice introduction with this picture. Right, can't change. There we go. So yeah, today I'm going to be discussing emergent space-time. But why are we discussing emergent space-time? Well, currently, of course, our best description of space-time comes from Einstein's theory of general relativity. But we don't think that general relativity is a fundamental theory. Instead, we think that it needs to be replaced by a new theory, a theory of quantum gravity, to describe the universe at very, very high energy scales, or very, very, very tiny length scales, in the regimes where quantum effects are supposed to become important. And maybe at these scales, instead of having a smooth space-time, we have something like that picture I just showed, so the quantum foam of these bubbles. So quantum gravity, it's not expected to describe space-time. So in the way that general relativity describes space-time, it's supposed to describe some new physics that somehow underlies space-time. And this new physics might be non-spatiotemporal to some extent, or at least it's supposed to differ very dramatically from what we understand as space-time according to general relativity. Nevertheless, of course, GR, with our conception of space-time along with it, should somehow be recoverable from this new theory of quantum gravity. Why? Because we know that we are in space-time, we use space-time and general relativity very successfully in describing all the universe. And so in the domains where we know general relativity works at these very large scales and low energies, it should continue to work, basically. The new theory shouldn't conflict with GR, where we know GR works. So the idea is that no matter what this new theory of quantum gravity is, it should link up to GR in a particular way, meaning that we can derive GR from it, we can derive an idea of space-time from whatever the more fundamental degrees of freedom are in this new theory of quantum gravity. So physicists have been looking for the theory for quite a long time, and we don't have an accepted theory of quantum gravity. What we do have are a number of incomplete approaches towards finding the theory, and I'll be discussing a couple of those today. So this is one reason why we want the theory of quantum gravity, to describe kind of the constituents of space-time, or more fundamental underlying theory of space-time. But there's another place where we expect quantum gravity to be important, where we expect general relativity breaks down as well. So not just at these short distance scales, but also in the very early universe. So of course, we have this picture of the expansion of the universe from the Big Bang here. And the idea is that we have our theory of general relativity, and we put in observations from cosmology and astrophysics. And then we run the equations backwards in time, going back to the very early universe. We see the universe, becoming more compact and denser until some point in the very, very early universe, our equations appear to break down, and we think that GR ceases to become reliable in these domains. And the reason for this is because we expect quantum effects to be important for describing the early universe after the Big Bang. So here too, we expect quantum gravity to be necessary for describing the very early universe. So there are two domains where quantum gravity is supposed to be necessary. Firstly, it's necessary for describing the physics underlying space-time. So this is kind of this picture, levels picture, I guess. So we move from this more fundamental non-spatiotemporal description of quantum gravity back up to general relativity. And this emergence, the idea is that there's no space-time here, but we have space-time up here at our level. And this usually in physics is known as synchronic emergence. We don't really want to use the word synchronic when describing emergence of space-time. So I've proposed to say hierarchical emergence, but of course that isn't ideal either because it's talking about scales. But anyway, levels-based picture of emergence. But then there's also another idea of emergence here. Because we're expecting quantum gravity to describe the physics near the Big Bang, and then maybe space-time doesn't exist here either. Instead, we have quantum gravity degrees of freedom, and then moving from this kind of prior non-spatiotemporal state to a spatiotemporal one, more like an evolution. This might be an example of what's normally known as diachronic emergence in philosophy of physics, but again, not the best term to use when we're talking about the emergence of time itself, possibly. So we can think of it in terms of flat emergence instead, or non-levels based account. Okay, so we have those two cases of emergence. I'll basically be discussing today, how do we understand this as emergence? And I'm thinking that we can have a quite unified account of emergence that covers both of these two cases. And I'll present this account of emergence and then show how it could apply in several cases of quantum gravity approaches. So loop quantum gravity, and in cosmology, so loop quantum cosmology, I'll discuss as well. Okay, so yeah, that was the intro. I'll start, this is where we're going to go for the rest of the talk. I'll say a bit more about what we mean by emergence generally, and then how it might apply in the case of spatiotemporal emergence. I'll then look at, firstly, what synchronic emergence usually is, and new account of synchronic emergence, and then look at how it applies in the case of quantum gravity. So that's the levels-based account. Then turn to the diachronic accounts of emergence, and look at how they apply in some examples of quantum gravity approaches, and then some conclusions. Okay, so what is emergence? This slide is just meant to show what emergence is understood as very, very generally. This one isn't my own account of emergence. This is kind of the very generic account of emergence. Typically, we think of emergence as an asymmetric relationship between two relata of the same nature. an emergent something we call E, and whatever it emerges from, the basis B. So that this general schema is what people work with, but then you have all different accounts of exactly what this means, right? But the general idea is that we have three conditions. There should be a dependence condition where the emergent E is somehow dependent upon, determined by, constituted by, generated by its basis. And yet E is also somehow novel and autonomous from its basis. Novel meaning it can exhibit striking features that B doesn't possess, and autonomous meaning that E is somehow unpredictable from, or irreducible to, or unexplained by B, or robust against changes in B. So for my purposes, I'm interested in emergence as being a relationship between physical theories. So E and B are going to be parts of our physical theories. And now we have the two different accounts of emergence. For synchronic emergence, E and B are supposed to represent different levels of description. So in my case, thinking about theories that might apply at a different range of length scales or energy scales. And typically here, the emergence theory E is supposed to apply kind of lower energies or larger distance scales than whatever it emerges from the theory B, which applies at higher energy or shorter distance scale. And yet these two theories are supposed to apply to the same system at the same time or otherwise under the same conditions. So the idea is that there's no change in the system except the level at which you're viewing it. So in physics, of course, the energy at which you probe the system is how we're thinking of it. Yeah, so I said B being higher energy and E being lower energy is a very typical way of viewing this. Contrast it with diachronic emergence. Here, E and B are supposed to describe the same system at the same level of description, so not at different ranges of energies or lengths. And they're supposed to apply at different times or otherwise under different conditions. So the idea here is that the system has undergone some change. Typically, B will describe it before, and then afterwards you have this emergent state after. So I really like this picture from Guy and Sartanea. So I've just copied it from them, basically, illustrating these two different ideas of emergent. So the idea is that at T1, you have some system that looks like this. At T2, you have some system that looks like this. Something has happened to it. And then if you're interested in synchronic emergence, you just look at the system at one time. So here, looking at it at T2, but viewing it at two different levels. So N1 and N2. So here, this, whatever this is, the state at N2, this higher level, has emerged from the state of the system at N1, the lower level. On the other hand, if you're interested in diachronic emergence, you don't change levels of description. You just stay on the one level, here just staying on the lower level N1, and you view the system at two different times. And then the state of the system here at T2 has emerged from the state of the system at T1. So that's the two different pictures illustrated. And as I said, both of these, I think, apply in the case of space-time emergence, but it's kind of a question without when we're talking about the emergence of space-time, it seems like maybe these two pictures just collapse into each other anyway. So yeah, quantum gravity is supposed to describe a synchronic or hierarchical account of emergence, being that it describes the physics at this lower level or higher energy scale. But it's also supposed to describe the physics near the Big Bang, and then we're supposed to have space-time emerge diachronically without looking at levels. So that more flat picture there. Okay, so let's now start by looking at the synchronic accounts of emergence, so the levels-based pictures of emergence. Normally in physics, it's common to think of it in terms of effective theories. So an effective theory is a physical theory that's supposed to apply only at a given level, basically a certain range of energy scales or a certain range of length scales. And the idea is that if you kind of push too close or too high energy, the theory breaks down. So it's not a fundamental theory, it's an emergent theory. So yeah, this is kind of the tower of effective theories here. We have a theory valid at level n. We can say it emerges from a theory valid at level n-1, so on. But the idea is that each of these theories is valid at a different range of energy scales, with this one being higher energy than this one, and this one being higher energy than this one. So an example of this are the analog models of space-time. This is a very nice picture of effective field theory. So very, I guess, schematically, imagine you have a fluid. So a fluid, and it's very coherent, it's valid. You have a theory of this fluid valid at high energy, its ground state. But the idea is that you can think of it in terms of like a crystal lattice. And when you hit this fluid with a small amount of energy, the atoms or the molecules in your fluid start to vibrate. And these vibrations, when you quantize them, you end up with phonons, so sound particles, basically. But these phonons, they can be treated as though they are living in their own space-time. They're basically acting like they're experiencing a curved space-time, even though the fluid itself, underlying it, is flat in its ground state. So we have this kind of flat space-time of the fluid, and then we have these phonons experiencing this effective curved space-time. And this is like completely generic. It's just a consequence of the linearization procedure you use to construct these effective theories. We end up with this Lagrangian that can be written as the sum of two terms, with the effective theory here describing the phonons, and this one describing the ground state of the fluid. So yeah, what you see then is that this effective theory is talking about a curved space-time, and this is a generic feature of the linearization process of these models. So we have an emergent space-time, but the thing is too, is that it's only effective, meaning that is valid at low energies. And if you kind of push too high, you're increasing the frequency of these phonons, and eventually they're going to get wavelengths comparable to kind of the lattice spacing between the atoms here. They're basically, at some point, if you push too close, it's going to collapse because these phonons will be able to detect basically the underlying fluid now. And then you won't have this effective theory anymore. You'll just have the theory describing the fluid. So it's interesting too, because these phonons, we treat them as emergent, but they're really nothing other than the vibrations of this underlying system. So it's a nice example of emergence, I think. So how does it fit this schema for emergence in synchronic emergence? So I've used this as kind of the exemplar of how we could understand synchronic emergence of space-time. Though, of course, in this case, we have space-time emergent from space-time. So it's a bit easier than space-time emergent from non-space-time. But first, we have this dependence condition. As we've seen, the theory describing the phonons, you construct it from the theory describing this ground state of the fluid. And the phonons are collective phenomena. They are just the low energy excitations of these underlying particles. So they depend, they're not going to exist without this underlying fluid existing. And yet we have a sense of novelty as well, because these theories are characterized by different degrees of freedom, and they have different symmetries. In particular, the theory of the phonons is Lorentz invariant, describing the curved space-time, whereas the theory of the fluid is Galilean invariant, describing the flat space-time. And this is used as an account of emergence according to Bain, Jonathan Bain. But I think we can also go a bit further and say there's a sense of autonomy. Here, the effective curved space-time is incredibly easy to obtain from a variety of different systems. So we can have different types of fluid, composed of different types of atoms or molecules, and yet end up with the same generic low energy behavior. So this behavior is quite autonomous or independent in a way from the behavior or the constitution or the theory describing this fluid. So this is how I've based the understanding of emergence here. So notice that this idea of dependence means that this low energy theory is derived from the higher energy theory. And the physics described by this emergent theory could also be said to supervene on those of B, if you like the idea of supervenience. If not, I think the dependence is shown by having this derivation using typical approximation techniques from effective field theory and physics. So this sense of emergence using this idea of dependence is emergence that's compatible with reduction. And as we'll see in quantum gravity, this is necessarily so. We also have a sense of novelty, where the physics described by the low energy or macro theory differs remarkably from that of the higher energy or micro theory underlying it. This idea of novelty is, it's symmetric. All it's saying is that E is different from B. And finally, we have an idea of autonomy, where the physics described by E is somehow robust against changes in whatever the microphysics is. And this means that if you just have the emergent theory, the kind of underlying, more fundamental theory that it emerges from is underdetermined. There are many different theories that are compatible with this emergent behavior. So this comes from, it's related to universality or multiple realizability. This emergent behavior is multiply realizable in different, more basic systems. And there's two different ways of this happening. Firstly, you can have different microstates or models of the more fundamental theory corresponding to a single macro state of E. So thinking about the relationship between models in statistical mechanics and thermodynamics, where you can have many different arrangements of the particles, different microstates, and yet they correspond to the same macro state in thermodynamics. But on the other hand, you can also have different micro theories corresponding to the same macro theory. That's what I mentioned before. You could have fluids of different micro constitutions. You can have different types of particles at the micro scale, which still give rise to the same generic behavior. So two different senses in which this theory is underdetermined. Right. So that's the idea of synchronic emergence that I want to work with, but how can it apply in the case of space-time? So generally, as we've seen, we expect, or it's a necessity, that any acceptable theory of quantum gravity is able to recover space-time, was able to derive GR in the relevant aspects where we know GR works. So quantum gravity must be able to reproduce all the successful results of GR. And this is normally done by derivation or various approximations, where we believe GR is deducible in principle from the more fundamental theory. So all this to say that this dependence condition of the emergent space-time upon whatever quantum gravity is telling us is that it must be fulfilled. It's like no theory of quantum gravity is going to be accepted unless it has this sense of dependence. So we just take it for granted that whatever the theory of quantum gravity is, we have this sense of dependence. Even if it hasn't been fully demonstrated in any of the approaches we look at. They're working on it. So on the other hand, however, there's no requirement that our other two conditions for emergence must be satisfied. The underlying degrees of freedom, or the theory describing quantum gravity, it may be such that it's not that different from GR, though so far I've been saying that it should be. It's not necessary in the same way that this dependence condition is necessary. So it's not like guaranteed that GR or space-time will emerge from quantum gravity. But in many of the approaches, I think all of the ones I've looked at, it does seem like these conditions are satisfied. It does seem like there will be emergence of space-time. So I'm just looking at the example of loop quantum gravity now. Very quickly on loop quantum gravity, in case you, well, I guess this isn't going to help if you're not acquainted with it anyway, but it's a canonical quantization of gravity, which means you have to put GR into Hamiltonian form, splitting space and time apart, and then quantizing space. So basically, to do this, you have to set up the theory in terms of these constraint equations, in terms of loop variables. And the constraint equation, which is supposed to describe the dynamics of the theory, is difficult to solve. So the part of loop quantum gravity that I'm going to be discussing now is just working at the kinematical level and not at the dynamical level. Although loop quantum gravity does have ways of working out the dynamics, I'm not going to look into them here. But basically what the kinematics tells us is that we can imagine that loop quantum gravity describes blobs of space. So because we're not looking at the dynamics, we're just talking about space rather than space-time. So here are blobs of space, and they are represented by abstract graphs known as spin networks. So here's an example of this, where the nodes represent the quanta of volume, which are adjacent to one another if there's a link between them. So it looks like a spatiotemporal depiction, but it's not supposed to be. These are meant to be chunks of space. They're not themselves supposed to be in space. So how does emergence fit here? Well, as I said, starting with this dependence condition, it's not so clear how we get space and space-time back from these structures, but we can see indications. We've come about to construct these structures by working from space-time backwards, quantizing it. And it's supposed that there'll be a superposition of these spin networks, and somehow this will give rise to space-time. For the sake of this talk, as I said, if this is a contender for quantum gravity, it must be able to recover space-time. So we take it that there is this dependence condition satisfied. So let's now look at the novelty and autonomy. And the novelty aspect has been really emphasized by Haggett and Wüthrich. And this, what I'm saying here is just from them. The autonomy part is more the part I'm emphasizing. So novelty, we're asking how different this emergent space-time is from this underlying spin network. And Haggett and Wüthrich point out many, many ways in which space-time is very different from that of the spin networks. And I'll refer you to their work on this. But you can see already this idea of thinking about superpositions doesn't give you a clear notion of geometry down here. So, and there's not a clear notion of time at this level either. Whereas obviously at our level, we're classical here, not speaking about superpositions, and we do have a notion of time. So the novelty condition is satisfied. But also I think we have a sense of autonomy here, because there are, many different microstates, different spin networks that could correspond to the same space-time. So in a way, the space-time is independent or universal compared to the underlying structures of the theory. And similarly, there are models down here that just don't give rise to space-time. So it seems like they are autonomous as well. So I think here we do have a good example of synchronic emergence of space-time in loop quantum gravity. So that's enough on the synchronic conception. Let's now turn to the diachronic conception. So looking at diachronic accounts of emergence in the literature generally, in particular, I was looking at Guy and Sartanea, who speak about transformational emergence. And I thought I could just look at their account and see if we could use it in the case of a space-time emerging from an atemporal Big Bang state. But their account makes reference to levels and time, so it doesn't automatically or easily translate into this case. But what do they say? They hold that E, the emergent thing, and B, whatever emerges from, are different states of the same system, again, interpreted at the same level, but at different times. E and B are supposed to describe models of the same theory. The dependence condition on their account holds because somehow this emergent state is just a process. It evolves from the prior state B. And yet, this emergent state is supposed to be novel and autonomous compared to B. It's supposed to exhibit new entities, properties, or powers that don't exist in the prior state B, and which furthermore are forbidden to exist in this prior state B, according to its own laws. So straight away you can see that this is not really going to work in the case of a space-time emergence. So what I thought was just go through and like cut out all the references to time. So we talk about the same system interpreted at the same level. We can't talk about these two states being related by a spatiotemporally continuous process of evolution. But then without having, well, even if you did have some sort of dynamics linking the two, it's not clear to me how that gives us dependence, right? Like just that you can go from one to the other. Why does that mean that one depends upon the other? In particular, how would you go from one state to the other without just conventionally saying this is the prior state or this is the emergent state? So it's difficult to get out a sense of dependence in this conception without having a time parameter or causation. But I think it could be, you know, Barron and Miller have been looking at non-temporal notions of causation, where E is somehow caused by B, without needing to talk about time connecting them. So I think that's one way in which we could say we have a dependence of E upon B without time. But also, as I said, you can think of supervenience in that hierarchical case where E supervenes on B. But then I think we could have an analogous idea of flat supervenience where E still supervenes on B. And I think this could give us a sense of dependence. Novelty, that part's easy. We can still have that without needing to talk about time, because all you need is just that E describes something new entities, properties, or powers that don't exist in B. Because it's just meant to be relative and symmetric, just the ways in which E and B differ from one another. But unlike with Gay and Sartanea, I don't think we need this strong sense of forbiddenness or underivability. I think weak novelty is enough, just saying that these two states differ from one another. And this is also expressed by Sheikh as well. So let's look at a nice example, very standard example of diachronic emergence. Though I should say Guy and Sartanea don't count this as diachronic emergence because it doesn't have that strong underivability or forbiddenness aspect. But for my purposes, as I said, we're going to need some connection between the two states, and having derivability or something like this is necessary. So the example of ferromagnetism as generic symmetry breaking phase transition. So here we're thinking about it in terms of the two levels, right? You start off with some material, and above particular temperature, known as the Curie temperature, your system is not magnetized. And that's because on the micro scale, if you zoom in, all its spins are randomized. However, once you move below the Curie temperature, the spins align in a particular direction in line with your external magnetic field. And the symmetry is broken. Here, the state was symmetric because they were all randomized. You could like imagine turning it in different directions and it's going to look the same random anywhere. Whereas now it has a preferred direction. So this symmetry is broken. And then of course, back at your macro scale, you're holding this piece of magnet. It's now possessing a net magnetic moment. The material is magnetized. So this is a symmetry breaking phase transition from the non-magnetic phase to the magnetic phase. So how does this fit into the schema for diachronic emergence? Well, as you recall, for diachronic emergence, we talk about E and B as being different states of the same system at the same level, and being different models of the same theory. So here we're just looking only at the micro level, just on the one level here. Do we have a sense of dependence? This was a tricky one again. Like I'm saying, this idea of dependence without time is quite tricky. So I'm thinking there could be a sense of flat supervenience where we don't have a change in this emergent state unless there was a change in the B state, not vice versa. But I'm not fully convinced of this, but it seems like it could work. Nevertheless, we definitely have some novelty and autonomy. We've seen, of course, that B is a state where there's no preferred direction, symmetric. And then the emergent state is one where we do have this broken symmetry. So they're very different from one another. And we also have a sense of autonomy. So this state can arise from many different microstates, many different random arrangements of these spins will nevertheless result in the same emergent state E. So if you're only looking at this emergent state, you don't know which particular microstate it came from. Your theory is underdetermined given the emergent state. So yeah, I think this is meant to be the example of diachronic emergence without time. So let's now look at that example and apply it to some examples from quantum gravity. And a really straightforward picture of this comes from pre-geometric approaches to quantum gravity. The one I'm presenting here is known as QuantumGravity because of the graphs. And here, space-time is supposed to emerge in a symmetry breaking phase transition, very directly analogous to that magnetic phase transition I presented. So it's known as geometrogenesis. So I should point out immediately, these approaches do have time. So this phase transition is a process in time. It's just the emergence of space that is presenting. So kind of before space, we have this maximally connected graph. We have these on the nodes, but the idea is that each node in the universe is connected to every other node. So this means that there's no conception of locality or geometry because everything's just connected to everything else. It's kind of just a lump, I guess. Except you can't think of it being a lump anywhere in space-time. But it's symmetric because you can see it's invariant under the permutation of the vertices. We can just swap these around and it's going to look the same. And then the idea is that the universe cools down after the Big Bang. Some of these links get broken. So some of them drop off, and what you end up is, a graph with many fewer connections. So it's no longer symmetric, but now we have this corresponding notion of geometry. We have some locality here. It's not just everything's connected to everything else. It's particular things are connected to particular other things. So yeah, I think this completely analogously to the case of the magnetic phase transition, it carries over again. We have the emergent space coming from a state without space. And we could say that the emergent state depends somehow on its basis B, the prior state. We have a sense of novelty, again, with this one being symmetric and this one presenting different symmetry. And we also have a sense of autonomy because this is very, very generic. This state doesn't depend on kind of particulars of the theory of the model. All it depends upon is the symmetry breaking pattern. So it's the emergent state is autonomous from this other state B. So yeah, I think that's a very straightforward example of diachronic emergence of space-time. But of course, that one's a bit of an easy one because there is a notion of time, though I've tried to not make use of it in describing the emergence. So the second example I'd like to present is in loop quantum cosmology. As I said, the dynamics of loop quantum gravity isn't so well understood. So in loop quantum cosmology, they just really simplify the system by making these very strong assumptions. You're just assuming that space is everywhere, isotropic and homogeneous, which means that you're basically just left with just one degree of freedom in your theory, which is supposed to be something corresponding to the scale factor A. Resulting very simplified dynamical equation, you can work with it, treating this one degree of freedom as the time variable. And you basically, start from the universe now and then run the equations back. And as I said before, what would normally correspond to, the universe getting very, very hot and dense and then turning into a singularity. In this model, I should say, this isn't generic of loop quantum cosmology. This is a very special class of models where this happens. But what you find is that the universe gets, hotter and denser, but it doesn't turn into a singularity. Instead, you can travel through the singularity. And what do you find? So the idea here, this is supposed to be like our universe here, and then we're running the equations backward. And so you see this triangle is getting smaller towards the tip. It's supposed to represent the contraction of our universe. And then at some point it gets maximally contracted, which would be the Big Bang. But in these models, you can still run through the Big Bang. You're not through a singular state anymore. But what you find is that you're now describing a universe that might be called a mirror world. You see it here. You're back into a universe that's expanding out again. So it's a big crunch followed by a re-expansion. So people call it a big bounce. And this is the standard interpretation of these kinds of models as being a big bounce. But Huggett and Wüthrich, though, think that this doesn't work as a big bounce because some of the models, again, they're talking about particular ones, feature a signature change, meaning that there's no continuous notion of time that you can run. Like in my picture here, this was meant to be the time arrow that you can just keep running through. They say no, because in this intermediate state, there's actually no sense of time anymore. We don't have that parameter varying that we were treating as time. So they say this one, this little dot I've drawn here is just meant to represent a purely spatial state with no time. So Huggett and Wüthrich look at this and they think, well, you know, we're talking about entropy and we always put time with the expansion of the universe, right, as going away from the Big Bang. So it's more natural then to interpret this as two universes coming out of kind of one non-temporal state. So rather than one coming in, crunching, and then re-expanding in a big bounce, they say, no, it's some atemporal state, and then bam, we have two universes emerging from it. And they call it the temporal emergence of space-time. But I was interested in how this actually fits my schema. How can we understand this as emergence? And I think it's already very difficult because we have those two different interpretations. What are we saying emerges from what? Are we saying that we have two expanding universes emerging, so space and time emerging from a non-spatial state? Or are we talking about in the other model? Well, could we say that the non-temporal state emerges from the space-time state? So it's quite, we have these different interpretations and already it seems a bit ambiguous how we could say which one emerges from which. So I will just take it that we want to describe the universe after the Big Bang, the spatiotemporal universe, emerging from this purely spatial state with no time, so that little dot state. We'll take that as the basis. But yeah, again, how do we say that this spatiotemporal state depends on the non-temporal one? It seems quite artificial. We definitely have novelty because we've got one state where we have time and one where we don't have time. But do we have autonomy? You know, how does it depends on how one depends upon the other. So this is a bit open whether we can call this emergence. Huggett and Wüthrich do put forward an even more speculative claim of how we could understand the dependence condition, which I think is interesting and could work. Treating this non-temporal dot region as coming before space-time, if we can extend time-like curves kind of in the effective direction to the non-temporal region in the past, but not in the future. And then they say, then we could consider this initial point as a time from which the later state evolved. But of course, this requires a dynamics, which we don't have. Yeah, I'll leave that to you to read. So I think this could work as a dependence condition, treating this non-temporal region as coming before the emergent space-time, if we can have this picture, treating them as an initial time. But again, to say we have autonomy, it would depend how sensitively this emergent space-time depends on this initial state. However, if we're talking about models with a scenario of inflation, this could give us a mechanism for autonomy as well, because basically with the inflation, it washes out all the details of the initial state, and it makes more of a generic universe at the end. So I think if it does support inflation, then we could have a sense of autonomy as well. So this could plausibly, but this is so speculative. Yeah, we're just imagining ways where it could be interpreted as emergent. Okay, so that was it. Just in conclusion, the synchronic and diachronic versions of emergence, I've suggested having the emergent E derivable from B or supervenient from B. Novelty, they're both strikingly different from one another. And a sense of autonomy, where we have the emergent state being very robust against changes in the basis state. Or if you're just given the emergent state, you can't, the basis state is underdetermined, or the basis state is under, basis theory is underdetermined due to a sense of multiple realizability. And I think analogously it works in both cases. So I think we can understand both forms of emergence in the same general schema, and that it fits with our ordinary ideas of emergence in philosophy and physics generally. We could go further and say, why am I even distinguishing the two? Because at that point, it doesn't make sense to even distinguish them. So I think that's a pretty valid thing to do as well. So I've presented two examples of synchronic emergence of space-time, one being these analog models of space-time with the fluids, and also GR space-time emerging from loop quantum gravity. And I've presented some possible examples of diachronic or flat emergence of space-time, analogous to these symmetry breaking phase transitions. And plausibly, we can have an atemporal emergence of space-time in the quantum cosmology, as Huggett and Zutrick describe, but just to emphasize that part's pretty speculative. Okay, yes, I've talked a lot. Thank you.
Yep. Thank you very much. So we can start with the Q&A. Ethan, you can start. Or...
Hi, thanks, Karen, for the really interesting talk. I'm really intrigued by the synchronic emergence of space-time. I'm wondering, is there a reason why we should think about the relationship between space-time and the non-spatiotemporal structure as emergence? Because, for example, wouldn't a relationship like parthood just do?
Yeah, I think that's fair. People just want to understand it as emergence in a way. So I was kind of interested in how we could understand it as emergence, but I don't think it necessarily has to be understood in that way. And maybe there are other relations that also work. But yeah, I think there is definitely a sense in which we can describe it as emergence, as I showed. But yeah.
All right, thanks.
Okay, I can ask something myself. So why would we, like, I know that as a matter of fact, people use emergence for both diachronic and synchronic, but why would we like to put them in the same category? Like, for me, it's quite clear that they represent like different things and different stuff. And for instance, every time I hear people speaking about diachronic emergence, the dependence relation is always kind of not
exactly.
so clear to me. So yeah, why would we want to have both in the same category? Or
Yeah. I mean, I think when we're talking about emergence, I mean, for me, I think this dependence condition is pretty necessary part of it, though some people debate it. But I don't see how, I think it should be an asymmetric relation, and then you need some sort of dependence to give you that asymmetry. But yeah, when the dependence is so hard to make sense of in the diachronic case, I'm not sure. Yeah, and you could see in the talk that was the bit I was a bit like, I'm not so sure about this. But insofar as we want to, or are interested in seeing how it could be understood as emergence, and to fit in this more general scheme of emergence, I think this is one way of doing it. But yeah, I share this question of why we would need to put them together. But then again, in this particular case of space-time, like we're no longer talking about having levels anymore, because that's already I skimmed over that part too, but talking about levels, you're already talking about distance relation or energy scales. It seems already to have some notion of space in it as well. And then getting rid of that, it seems we don't have this distinction between the two accounts anymore either. So yeah, I could have maybe just started with a general account instead of starting by looking at the two separately.
well, but still, like I still have the intuition that they are like different things, and even in the quantum gravity literature, I'm thinking now in Oriti, and when he thinks about geometry genesis as a process, not in time, but that there is a before and after.
Yeah.
In some sense, the idea that there is a distinction is.
Yeah, that it comes into being. It didn't exist before the Big Bang, and it's come into being. That seems. I mean, it seems natural to want to think of that in terms of time emergence. I mean, you guys are the expert group on this whole time emergence thing, right? How to make sense of this conceptually.
Okay, thank you. Luciano, go ahead.
I want to, hi Karen, thanks for the talk. It was very interesting. I want maybe to clarify something for myself. When we are talking about the diachronic emergence, we seems to have like the very concept of time there, like something happened after and then. And it seems to work, for instance, in quantum gravity. I'm not much familiar with the theory, but it seems that time is something more fundamental than in other theories as loop quantum gravity or group field theory. So it seems that the diachronic emergence needs, in some sense, time being a fundamental aspect of the theory. I don't know if a degree of freedom or what, but time is in there as something happening. Why do you think we insist on theories which do not have time as fundamental entities? For instance, loop quantum cosmology as being part of diachronic emergence instead of trying to classify them as synchronic. Because, for instance, when you talk about the bounds, but if you cannot define the time in that particular point, which is the singularity, then it has sense to speak about the contracting and expanding phases of the universe, or we need to focus more on how do we get rid of the singularity and how can we go out that singularity point, which does not know time. Because if you don't have a notion of time, it seems to me quite more near to group field theory, where the geometrogenesis, it seems to be classified as a synchronic emergence instead of a diachronic emergence. So why do we try to categorize this in these non-temporal entities, forcing them to be diachronic?
Yeah, I mean, I was just trying, because it seems pretty, like, it seems like we just want to understand the universe beginning from something and then coming into time, into space-time. And then that kind of picture, I mean, that's how I came into it, how I say that. It seems like just a natural starting point to think of this distinction, because it definitely makes sense for us. Yeah, so you can see my strategy. I started with known examples of synchronic and diachronic accounts in emergence, and then seeing how we could translate them to the spatiotemporal case. So I think it can be done, but your idea is saying, why do we need to kind of shoehorn it in this way or understand it in this way? Yeah, and to that, I would say I kind of agree with you. And in a way, my paper is more, I guess, a bit reactionary, because I was looking at the way Hagen and Vutric had done it, and then kind of wanting to understand how that is emergent, because they're talking about atemporal emergent, meaning that it's supposed to be somehow temporal rather than this hierarchical structure. But I agree, yeah, like I was just saying, not having this idea of scales or time anymore, why would we bother distinguishing them from the outset? So maybe that's where I should have arrived at by now, but just starting from the more intuitive two cases of emergence that we have more generally in physics. Yeah, but I think at the end of the day, this is, I can see the point, and I'm trying to maybe collapse the two, but then it's still, if we do, you can see that it still has this account of emergence without needing spatial temporal notions there. It's the idea. So it should apply to group field theory as well.
And then I have another question, because for me it's more clear, the diachronic emergence, but when we start talking about synchronic emergence, we are referring all the time to notions I don't think they work in the quantum. For instance, when you say things happening at the same time, when we are trying to define a temporal emergence, okay, we are clear about that. That does not work. But other like statements of for example, happening under the same conditions. No, if we are trying
with this one.
so for me, it's very difficult to make a categorization of the synchronic emergence, in the sense that I can see the picture, so I can imagine a level picture, but I cannot familiarize with the concepts of, for instance, same energy or scales, if we are dealing with things like in the quantum does not have notions of geometry or of energy or these kind of things.
Yeah. But I think here is maybe, well, of course it's difficult with quantum mechanics generally, how we go from the quantum to the classical, but ignoring, and I think that's probably where what you're hitting at, that I can't answer that problem. But I think the idea of energy scales in that picture isn't so different from what we normally do in physics, because in that case we do have, when we're working at this higher level or the lower energy scales, we can say it at this level, and then we can just use techniques like renormalization group to kind of move to higher and higher energies and find this more fundamental theory. So I don't think that one is so problematic until you bring in that, if you're talking about quantum superpositions and things like this.
Okay. Thanks.
Okay, I have some more questions if anyone else, if no one else has. Okay, so in your slide about quantum cosmology, you said that you are using the scale factor as a time variable. And then you're saying, oh, we are studying how the universe expands and contracts, but if the volume of the universe is what you're using as a time variable to say that it expands to the future, it seems to be just true by definition, you know?
Yeah, exactly. So yeah, that part was from Hagen Vutric, and I think that was their point, that you need to make this conventional, and this, we're taking this as, because you know, we can run this variable either way, and which one's depending on which one's the future and what. But then it's just conventional to take it as going in the expanding.
Yeah, but I think there are some other models in which they take some scalar field or something like that to be the time variable.
Yes.
And then I can see how you can speak about the universe expanding, contracting, bouncing, or whatever. But
yeah, I totally agree. Like these models that I just described, it does seem pretty weird. It does seem like you need an extra scalar field to act as the time variable. I agree. So I think we should be looking at those models instead of these other models without it.
okay, yeah. And the other thing I had is that your account seems to be, to me, like describe pretty well what physicists mean when they use the term emergence. Like, okay,
yeah,
there is some
because it has that
novelty,
reductive or derivation aspect. Yeah.
right? But the other senses of emergence maybe had to do with the emergence of the mind over the body, or like they have like a stronger philosophical implication. So does your project of defining emergence do any philosophical work for any other philosophical debate, or is it only just descriptive, which is fine, it's already good enough?
Yeah, you can tell I'm just working kind of at the theory level in a way, and kind of to take that extra step of what it tells us about what's emergent. No, I haven't done that, and I don't think we're really, I mean, you talked to Baptiste, right? He's good at this sort of thing, with the metaphysics stuff. I mean, I'm trying to at least have some, this idea of autonomy, to try and do justice to what's meant by emergence. But of course, it's not a strong autonomy. It's not like, yeah. And I kind of don't believe we need this strong autonomy. Like Gay and Sartney, like I said, they didn't like my example of phase transitions as being emergent, because they're saying that's just straightforward derivation. We can get from one to the other. But I don't think that's a problem. I think, you know, and I've been accused of making emergence ubiquitous, and then it's no longer special. But I think the opposite. I think the fact is we have these systems with the multiple realizability and robustness of the emergent phenomena. And I think this is really interesting, even if you can derive one from the other. That doesn't make it any less interesting. It shouldn't kill all this like mystical aspect. In fact, it should make it more interesting. The fact that it is ubiquitous, we can ask how and why is it everywhere, instead of looking for something that's very special. Yeah, so that's my thoughts on it.
Okay, thank you very much. Is there any other question? If there isn't, we can just thank you again and It was a great talk. Thank you very much.
Yeah, really good meeting you.